Hello everyone. Today I am going to talk about quantum kernel methods which sit at the intersection of machine learning and quantum computing. The key idea is very simple. We use a quantum computer only to measure similarity between data points, and then we let a classical machine learning algorithm to do the actual learning. So this is a hybrid approach, quantum where it helps and classical where it is already strong. Let me start with something very familiar. Many machine learning algorithms do not actually care about the raw data values. Instead, what they care about how similar two data points are. Typical questions are, is there a new point closer to class A or class B? And another approach is what is unsupervised type of learning is how similar is it to what I have already seen. A very important example is the support vector machine or SVM. In an SVM, the decision boundary depends only on pairwise similarities between the data points, not an explicit feature value. So the problem is directly comparing points in the original data space often fails, especially for nonlinear data. That's why choosing a good similarity measure or kernel is absolutely central to performance. To fix this problem, machine learning uses something called as feature map. Instead of working in the original space, we map data into a higher dimensional space where pattern becomes easier to separate. The right side figure actually shows the two particular data points are mapped to a 3D data point, and then we can easily separate them through a decision surface. Instead of now explicitly constructing this high dimensional feature vector can be extremely expensive. This is where kernel tricks comes in. So a kernel computes the inner product between two feature vectors without ever constructing them explicitly. So the SVM never sees the feature vectors, it only sees their similarities, and classical kernel like polynomials or RBF kernels do this implicitly. Now the question we now ask is, can quantum mechanics give us even richer feature space? So why quantum feature space are powerful? This is where quantum computing becomes interesting. Suppose we encode data into a quantum circuit acting on n qubits, and the corresponding feature space is the quantum Hilbert space, whose dimension is a complex space with 2 to the power n. That means the feature dimension grows exponentially with the number of qubits. Importantly, we never store or list these features, they exist implicitly as quantum states. A carefully designed quantum circuit can therefore generate extremely rich, highly entangled feature representation that are very hard to simulate classically. So quantum computers act as feature generators, not classifiers. Now let us see how quantum kernel is actually computed. Consider two classical data points xi and xj, and each data point is encoded into a quantum state using same feature map circuit and producing the states xi xi and xi xj. The similarity between these 2 points is defined as the overlap between their quantum states. Operationally, this is evaluated using a quantum circuit where we first apply the encoding for one data point and then apply the inverse encoding for the other, and finally perform a measurement. The outcome of this measurement directly estimates how close two quantum states are. As a result, the kernel value becomes physically measured quantity obtained from quantum inference rather than purely algebraic computation. The right side we show a diagrammatic visualization of quantum circuit for estimating quantum kernels. After running the circuit, we measure the qubits. We focus on probability of measuring all zero state. The probability turns out to be exactly squared overlap between two quantum feature states, and the number is our quantum kernel value. By repeating this process for all the data points, all pair of data points, we construct the kernel matrix. And now something important happens. At this point, quantum computer job is done. So the kernel matrix is passed to completely classical SVM, which performs training and classification exactly as usual. So quantum computes the how similar two data points are, and then we shift back to classical machine learning. And this separation makes quantum kernel very practical for near-time devices. So let me summarize the main messages. Kernels are fundamentally about measuring similarity of two different data points. So quantum kernel measures similarity using quantum state overlaps in exponentially large feature space, which are sometimes classically hard to simulate. So quantum circuits act as implicit feature maps, not a learning model. And finally, quantum kernel integrates seamlessly with classical SVMs, making this a clean and realistic hybrid approach. So quantum kernel methods are not replacing classical machine learning, they are about enhancing it where classical computing struggles most. Thank you.